Hello everyone, it's my honor to introduce our work, mmWaveFlow, a unified framework for the enhancement and generation of mmWave human point clouds. Human sensing is a core field in computer vision, covering various tasks from pose estimation to action recognition. Recently, mmWave radars have gained attention for human sensing because they are privacy-preserving, low-cost, and are robust to dark and occlusion scene. However, from our perspective, two core challenges remain in mmWave-based human sensing: data quality and data quantity. mmWave point clouds are inherently sparse and noisy, and the lack of large-scale annotated datasets limits their practical use in real-world tasks, such as pose estimation and action recognition. Previous works typically treat these two problems as separate tasks. To mitigate data quality issues, existing methods enhance mmWave point clouds to LiDAR-like density using diffusion-based methods. To mitigate data quantity issues, existing methods generate mmWave data via mesh-based physics simulation, optionally refined by neural networks. Our key insight is that both tasks can be framed as a transport problem between two data distributions. Enhancement transports mmWave data to dense point clouds, while generation transports dense data to mmWave point clouds. Therefore, we propose a unified model that learns invertible bidirectional transport to achieve both enhancement and generation. Flow matching model offers exactly the capability we want. Unlike traditional diffusion models, which start from Gaussian noise, flow matching model learns a velocity field that defines an ordinary differential equation between any two distributions. This property naturally aligns with our motivation for invertible transport. Based on this, we introduce mmWaveFlow, a unified framework for mmWave point cloud enhancement and generation. As shown in the figure, we first use a VAE encoder to project inputs from different modalities into latent tokens. A cross-modal latent alignment module then aligns the semantic information across these tokens. Next, a flow matching module learns the transport between tokens from different modalities. Finally, a VAE decoder can project the tokens back to the point cloud space. Next, I will introduce our two key modules, cross-modal latent alignment and origin-aware flow matching. The VAE encoder aligns token shapes but not token semantics. Since point cloud tokens are instance-dependent, tokens with the same index may correspond to different body parts across samples, as shown in the figure on the right. This violates the alignment assumption of flow matching, causing element-wise interpolation to mix unrelated features. Our cross-modal latent alignment fixes this in two ways. First, shared query cross-attention projects tokens from different modalities into a unified feature space. Second, contrastive learning that pulls tokens with the same index from different modalities together and pushes others apart. Besides, previous work removes the condition from the velocity field to improve efficiency. However, this condition-free formulation suffers from latent path crossings, where different trajectories intersect in latent space but require different transport directions. At these intersections, the model receives conflicting supervision and averages conflicting signals, leading to biased transport. The upper part of the figure on the right provides a simple visualization of this issue. We mitigate this with origin-aware flow matching, which conditions the transport on a randomly sampled origin source or target. This enables the model to distinguish crossing trajectories and learn invertible transport. We evaluate mmWaveFlow on three public datasets. As shown in Fig 1, on both tasks Densitocean wave and mmWave to DensitoWaveFlow achieves lower chamfer distance and Earth movers distance. Visualizations further demonstrate that mmWaveFlow produces realistic point clouds for both enhancement and generation. For downstream tasks, we see clear improvements from different data augmentation strategies. First, using our enhanced mmWave data, the MPJPE for human mesh recovery dropped by up to 9%. Second, by generating additional training data to augment the limited dataset, action recognition accuracy improved from 0.661 to 0.790. Ablation studies confirm that both latent alignment and origin-aware flow matching contribute significantly to the final performance. That's all. Thank you. If you have any questions, feel free to contact me.